I have a container made of perfectly insulated material. What I mean by perfectly insulated is that there's going to be no energy exchange through the walls. Matter of fact, we're going to seal it off at the top also, so we'll magically be able to put something into it, but the energy is going to stay in here. And we have water at 20 degrees Celsius. Let's make it 25 grams of water. I'm magically going to put in an aluminum cube and 50 grams of aluminum at 60 degrees Celsius initially. So this is my initial temperature for the water, and this is my initial temperature for the aluminum. So conceptually, what's going to happen? I take this, I have water at basically room temperature, and I stick a hot aluminum cube into it. What's going to happen?
The water's going to heat up.
And
The temperature's going to change. What temperature's going to change?
yes, to both of those things.
The cube will cool down.
Yes,
Yeah.
that's the other piece I was looking for.
Since the aluminum takes less energy is it to heat up or to change in temperature?
Change in temperature.
So would it cool down, would the cube cool down before the water ever heated up? If you put in a hot cube?
Oh, close. Your wording's off though. It's not, they will start changing at the same time. But the aluminum's gonna cool off more than the water will heat up. If you have the same amount of material, it will. Now the fact that I've got twice as much mass for the aluminum as I do water, it's gonna be a little bit different. But in this case, because the specific heat of aluminum is between 20 and 25% of that of water, but I have only twice the mass, the aluminum cube should cool off more than the water will heat up. Now, the reason why I wanted the other piece of it is the fact that I want to emphasize energy is conserved here. That I have energy flowing from the cube into the water. So I know that Q for the aluminum plus Q for the water is equal to 0. There's any energy that the cube loses, the water gains. And what is the formula for Q when we're talking about changing temperatures? Yep. So this is the mass of the aluminum times the specific heat of the aluminum times the change in temperature of the aluminum plus mass of the water. I'll just put W for now. Specific heat of the water times change in temperature of the water is equal to 0. The M's and C's we know. So mass of the aluminum is 50 grams. Specific heat 0.21. Thank you. Calories per gram degrees Celsius. Change in temperature, well, that's whatever that final temperature is minus the initial temperature, which is 60 degrees Celsius, plus mass of the water, which is 25 grams, specific heat of the water, which is 1 calorie per gram degrees Celsius, change in temperature, which is whatever the final temperature is minus 20 degrees Celsius is equal to 0. Now, putting the units in there just sort of clutters it up, but from a science point of view, the units do matter. However, we've now made it a math problem, so let's just write down the math problem here. I have 50 times 0.215 times T minus 60 plus 25 times 1 times T minus 20. That's the math problem. I do want to point out that our unknown, the TF here, my final temperature, it's the same for both. The aluminum is going to cool down until it's the same temperature as the water, or the water is going to heat up until it's the same temperature as the aluminum. That's what I can do in my head. That's 25. And that one is 10.75. Minus 16. So now we distribute. So I have 10.75 T minus whatever that is times 60. 645. Okay. Plus 25 minus 2500. Oh, 25T. Awesome. Distributing. So we have 35.75 times the final temperature minus 1145 is equal to 0, or 35.75 T equals 1145 divided by 35.75. Now, before we actually write down the answer, some of you, at least one of you, I suspect, has actually done it already, but from what we talked about earlier, I know the final temperature has to be between 20 and 60 degrees Celsius. It has to be. And because the aluminum gives up heat or gains heat, the temperature change requires less energy transfer, we expect the final temperature to be closer to that of water. So whatever it is, it should be between 20 and 60, and it should be closer to 20 than to 60. So it gives us a quick, dirty look at, does our answer make any sense whatsoever? And we end up with 32.02. All right, at least I knew I heard a 2 in there somewhere. Units?
Degrees Celsius.
And this, in essence, is what you're going to do in the lab. The difference between this and the lab, I mean, you're going to take water, you're going to put a cube into boiling water to get the cube up to the temperature of the boiling water. Then you're going to transfer it into cold water, taking the temperature of the water as you go, and so the temperature of the water should be increasing, and then it'll peak, and then it'll start cooling off because we don't have our perfectly insulated material. But you'll be looking to see where it peaks. And then from that, you're actually going to be solving for this, since you'll know the final temperature, but your unknown is going to be the specific heat of the material, and then you'll compare it to the bulk value. All right, so let's actually work through one that is closer to lab-like. Since this is going to be sitting in boiling water, it'll be close to the boiling point of water. And you know what? Instead of aluminum, we're just going to make this some unknown. Because I'm about to make numbers up, and I doubt if I'm going to get close to 0.215. So initial temperature of the metal. So instead of aluminum here, I'm going to put a little M for metal. So we have a piece of metal that's really close to the boiling point of water. We put it into our room temperature water, and the final temperature is 37 degrees Celsius.
So is that the final temperature of the water and the cube?
Yes, because the temperature of the water should be increasing as long as the cube is giving up heat. And then then when it peaks is when basically they're the same temperature, or close enough. Now do note from a mechanics point of view, I got a cube in boiling water. The temperature of it's been sitting in there for a couple of minutes, so the temperature of the cube is close enough to the temperature of the boiling water. When I transfer it, it will immediately, as soon as I bring it into the air, it'll immediately start losing energy into the air. So you need to transfer it as quickly as possible into the other water and cover up the other water as quickly as possible. So we have 50 grams times our specific heat of the unknown times the change in temperature, which is 37 minus 99 degrees Celsius, plus mass of the water, just 25 grams, times specific heat of water, 1 calorie per gram degree Celsius, times change in temperature of the water, which is 37 degrees Celsius minus 20 degrees Celsius, equals 0. So that's negative 62, and that is 17. Negative 3100 C, 425. And so my specific heat, we subtract 425 from both sides and then divide by negative 3100.
137.
137 units.
Calories per kilogram degree Celsius. Or grams, sorry. I don't know why I wrote kilogram.
So if you want to do kilograms, then you'd be multiplying by 1,000 grams per kilogram. So this would be the equivalent of 137 calories per kilogram degrees Celsius, if you wanted to do away with those pesky decimals. Now we can make this slightly more generic, and in the lab I do this. Basically we're solving for this right here. So you subtract this whole thing over to the other side, so we have mass of the metal times C delta T, C of the metal, delta T of the metal is equal to negative mass of the water, specific heat of the water, change in temperature of the water. And then we divide by the mass of the metal, the delta and the change in temperature of the metal. And so the specific heat of the metal is that right there. I think that's the way I have it written. It's also possible that I went ahead and just substituted a 1 in for CW. But I think I left CW there.